Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most mysterious questions physics has ever asked. Is time travel possible through black holes? Could the strange gravity of these dark giants bend time so deeply that the past becomes reachable? Could wormholes act as hidden tunnels through space-time? Or does the steady march of entropy quietly forbid such adventures before they ever begin? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into black holes, wormholes, and the nature of time itself. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Tonight, we won't rush. We won't throw equations at you or drown you in symbols. When physics becomes technical, we'll translate it into images. When mathematics draws sharp edges, we'll soften them into landscapes. We'll move slowly, like someone walking along the edge of a vast canyon at dusk, curious, careful, and unafraid. And so, as the universe slowly expands around us, we begin not at the edge of a black hole, but long before it formed. If you look up at the night sky, you see galaxies, great spirals of stars turning quietly in the dark. For a long time, astronomers assumed those galaxies came first. Stars formed. They lived. Some of them died. And from their collapsed remains, black holes were born. It seemed simple, natural, logical. But then the universe began whispering something unexpected. When astronomers peer very far away, which also means very far back in time, they see quasars. Quasars are brilliant beacons powered by supermassive black holes, and some of these quasars appear astonishingly early in cosmic history. So early, in fact, that there doesn't seem to have been enough time for a normal black hole, born from a dying star, to grow that large. Imagine discovering a skyscraper standing in the middle of an empty field, long before the surrounding city was built. You would wonder, did the city grow around the tower? Or did the tower somehow appear first? That is the cosmic chicken and egg question. Did galaxies give birth to black holes? Or did black holes help assemble galaxies around them? In the earliest moments after the universe began expanding, in that hot, dense state we softly call the Big Bang, matter was not arranged in stars or planets. It was more like a glowing fog, a thick, luminous mist of particles slowly cooling and spreading outward. As this fog cooled, gravity began its quiet work. Tiny variations in density, places where matter was just a little thicker, began to pull more matter inward. Over time, those clumps grew. The traditional story says that these clumps formed stars first. Some stars were enormous, far larger than our sun. When such massive stars ended their lives, their cores collapsed under gravity, forming black holes. Over millions and billions of years, those black holes merged and consumed surrounding gas, gradually growing into the supermassive black holes we see today. Objects millions or even billions of times heavier than our sun. But here's the puzzle. Some of the earliest observed quasars already contain black holes weighing 1 billion times the mass of our sun, and they appear less than 1 billion years after the universe began expanding. In cosmic terms, that's incredibly fast. It's like watching a sapling turn into an ancient oak tree almost overnight. So physicists proposed another possibility, something called direct collapse. Instead of forming a star first, Perhaps vast clouds of gas in the early universe collapsed directly under gravity, not into a shining star, but straight into a massive black hole. No intermediate step, no stellar phase, just a colossal cloud giving way under its own weight. To understand this gently, imagine a cloud so large and so dense that instead of forming individual raindrops, it falls inward all at once. There is no drizzle, only a sudden inward rush. In this scenario, a massive black hole could appear very early, acting almost like a gravitational anchor. Matter would gather around it. Stars would form in orbit. A galaxy would assemble, slowly swirling around this deep gravitational well. It would mean the heart formed before the body. Observations of small, faint dwarf galaxies add another layer to this mystery. Some of these tiny galaxies, containing relatively few stars, appear to host surprisingly large black holes at their centres. It's as if a small village were built around a skyscraper far too large for it. These clues suggest that black holes may not always be the end of a story. Sometimes they might be the beginning. And this matters for our question about time travel. Because if black holes were present at the very dawn of cosmic history, if they helped shape galaxies themselves, then they are not rare accidents. They are woven into the architecture of the universe. They are not cosmic mistakes. They are structural. To understand whether time could bend within them, we must first understand what they are in the grand design. Not monsters, not vacuum cleaners, but deep curvatures in the fabric of space-time itself. Places where gravity becomes so strong that even light cannot escape. In future sessions we will gently approach that boundary, the event horizon, the place often described as the point of no return. We will explore what happens to clocks near it, and whether falling inward could allow us to slip into another era. But for now, simply imagine the early universe as a dim, cooling ocean of matter, and in that ocean perhaps a few deep whirlpools formed very early, drawing everything gently toward them. Black holes may not just sit at the centres of galaxies, they may have helped galaxies come into being. And if they have been with us since nearly the beginning of time itself, then perhaps, just perhaps, they hold clues not only about gravity, but about time. If black holes may have appeared early in the universe, the next question becomes even more intriguing. What do we see today that might support this idea? Are there quiet hints scattered across the sky? Small clues hidden in faint galaxies? Astronomers have spent decades mapping the heavens with increasingly sensitive instruments. Projects like the Sloan Digital Sky Survey have catalogued millions of galaxies, measuring their light, their motion, and the subtle signatures hidden in their spectra. And among those countless galaxies, some stand out in a rather surprising way. There are tiny galaxies, dwarf galaxies, that contain far fewer stars than the majestic spirals we usually picture. Some are faint, almost ghost-like, yet when astronomers examine their centres carefully, they sometimes find evidence of black holes that are unexpectedly large. Imagine walking into a small countryside village and discovering, at its centre, a cathedral so vast it rivals anything in a great capital city. The scale feels mismatched. The heart seems too large for the body surrounding it. In cosmic terms, this mismatch suggests something profound. If a dwarf galaxy contains a black hole that is already quite massive, it may mean that the black hole did not simply grow alongside the galaxy. It may have been there first, or at least formed very early before the galaxy fully assembled. To understand why this matters, we need to gently consider how black holes grow. A black hole increases in mass when matter falls into it. Gas, dust, stars, anything that crosses its boundary adds to its weight. Over time, if enough material spirals inward, the black hole becomes heavier. In some cases, it can grow to millions or even billions of times the mass of our Sun. Now, the Sun itself weighs roughly 2 billion kilograms. That number is so large it loses meaning when spoken quickly. So instead of focusing on the number, imagine stacking 2 billion bags of sugar, each one weighing a kilogram. That is the mass of just one Sun. A supermassive black hole might weigh 1 billion times that. The surprise is not that such enormous objects exist. We know they sit at the centres of large galaxies, including our own Milky Way. The surprise is finding relatively hefty black holes and galaxies that are otherwise small and undeveloped. It raises the possibility that black holes may act like seeds, but seeds that are sometimes heavier than the tree that grows around them. If that sounds strange, consider planting a seed that already weighs as much as a young sapling. As it draws nutrients from the soil, it doesn't just grow with the tree, it shapes how the tree grows. The trunk curves around it, the roots adjust. The entire structure adapts to the presence of that initial mass. In a similar way, a black hole's gravity influences the motion of nearby gas. Gas clouds drifting through space feel its pull. They begin to spiral inward. As they do, they compress, heat up, and sometimes form stars. The galaxy begins to take shape, not randomly, but guided by the deep gravitational well at its centre. And this gravitational well is not like a vacuum cleaner sucking everything indiscriminately. That is one of the most persistent myths about black holes. If our Sun were magically replaced by a black hole of equal mass, Earth would not be pulled in. Our orbit would remain almost exactly the same. Gravity depends on mass and distance, not on whether that mass is luminous or dark. So black holes do not devour everything in sight. They influence, they guide, they curve the paths of nearby matter. This subtle influence suggests that in some cases, black holes may have played a role in organising galaxies. Rather than being mere byproducts of stellar evolution, they might be foundational structures, like wells dug first, with villages gradually forming around them. There is another layer to this story. Some of the earliest quasars, those brilliant beacons powered by feeding supermassive black holes, shine so intensely that they outshine entire galaxies. They are visible from across billions of light years. When we observe them, we are seeing light that left them when the universe was very young. The fact that such massive black holes existed so early means they must have formed and grown rapidly. The traditional model of slow accumulation through stellar remnants may not be enough to explain their size. Direct collapse, where vast gas clouds fall inward all at once under gravity, becomes an attractive possibility. In that picture, the early universe was not just forming stars. In certain regions, it was forming immense gravitational anchors from the very beginning. And if black holes were present at such early stages, if they helped gather matter into the first galaxies, then they are not rare cosmic accidents. They are woven into the blueprint of structure itself. This shifts our emotional relationship with them. Instead of viewing black holes as catastrophic endings, we can begin to see them as central organisers, deep wells around which cosmic cities form, quiet hearts beating at the centres of swirling star systems. And this perspective is important for our deeper question. If black holes are structural features of the universe, if they have shaped galaxies since near the dawn of time, then their relationship with time itself may also be structural, not a glitch, not an anomaly, but part of the architecture. Soon we will gently move closer to one of these immense wells. We will approach the boundary where space curves so steeply that even light struggles to escape. We will explore what happens to clocks near that edge and why time itself begins to behave differently. But for now, simply picture the early universe once more. A dim, expanding sea of matter. In certain regions, gravity gathered itself more tightly. Deep wells formed, and around those wells galaxies slowly took shape. Sometimes the heart comes first. Sometimes the well is dug before the town appears, and sometimes the universe surprises us by building its foundations in darkness. Now that we've imagined black holes as deep wells around which galaxies gather, we can slowly move closer to one, not falling yet, just drifting nearer, like a leaf carried by a current toward the sound of distant water. If you were approaching a black hole from far away, nothing would seem unusual at first. Stars would orbit it, light would bend slightly around it, and space itself would curve gently inward. From a distance, it behaves like any other object of the same mass. It does not reach out with invisible hands, it simply curves the space around it. To understand this softly, imagine space not as emptiness, but as a flexible landscape. If you place a heavy ball on a stretched sheet, the sheet dips. Smaller balls rolling nearby follow curved paths because the surface itself is curved. They are not being pulled by magic. They are simply following the shape of the surface beneath them. In a similar way, a black hole curves the fabric of space and time, and the closer you move toward it, the steeper that curve becomes. There is a particular boundary around a black hole that physicists call the event horizon, but instead of focusing on the technical name, imagine it as the edge of a waterfall. Upstream from the waterfall, the river flows calmly. A swimmer can paddle against the current and make progress. But as the water approaches the edge, it begins to flow faster and faster. At some point, the current becomes so strong that no matter how hard the swimmer tries, they cannot move upstream anymore. They're carried toward the edge. The event horizon is like that point in the river. It is not a solid wall. It is not a fiery surface. It is simply the place where the flow of space inward becomes faster than anything can move outward. Even light. Light is the fastest traveller we know. Nothing can outrun it. In ordinary conditions, if you throw a ball upward fast enough, it can escape Earth's gravity. That required speed is called escape velocity. For Earth, that speed is about 11 kilometers per second, roughly the distance of 11,000 meters every second. But a black hole is different. Near its boundary, the escape velocity exceeds the speed of light itself, and because nothing can travel faster than light, nothing can climb back out once it crosses that edge. When physicists describe this with equations, they write relationships between mass, gravity, and distance. But instead of symbols, let's imagine something simpler. Picture trying to run up an escalator that is moving downward. At first, you can make progress. You run faster than the escalator moves. But if the escalator speeds up beyond your maximum sprint, you can run as hard as you like. You will still move downward. At the event horizon, space itself is like that escalator. It is flowing inward so quickly that even light cannot run upward against it. And something remarkable happens to time near that boundary. If a distant observer watches someone fall toward a black hole, they do not see that person cross the event horizon. Instead, they see the falling clock tick more and more slowly. The closer it gets to the edge, the slower it appears to move. The falling object also appears to dim and redden. Like climbing away from strong gravity loses energy. Its wavelength stretches, shifting toward red, like a sunset slowly deepening. To the distant observer, the infalling traveller seems to freeze at the edge, fading away gradually, never quite disappearing. But from the perspective of the falling traveller, something very different happens. They do not feel time slowing. Their own heartbeat continues normally. Their watch ticks at its usual rhythm. They cross the boundary without noticing any sudden wall or flash of light. This difference between perspectives is one of the most beautiful and unsettling features of general relativity. Two observers can describe the same event in radically different ways, and both descriptions can be correct. Time is not universal, it is local, It depends on gravity and motion. We already see gentle versions of this effect in everyday life. Satellites orbiting Earth experience slightly weaker gravity than we do at the surface. As a result, their clocks tick a little faster, not by minutes or hours, only by tiny fractions of a second each day. But those tiny differences matter. The global positioning system relies on precise timing. If engineers did not correct for this effect, GPS locations would drift by kilometers over time. So gravitational time dilation is not science fiction. It is measured, accounted for, built into the technology we use. Near a black hole, however, this effect becomes extreme. Imagine placing one clock far from the black hole and another slowly lowered toward the event horizon. The closer clock would tick more slowly relative to the distant one. If the difference in gravity becomes immense, the slowdown becomes dramatic. This is where time travel to the future becomes possible. If you could hover near the event horizon for a while and then return safely to a distant region of space, you would find that more time had passed for others than for you. You would have aged less. You would have travelled into their future. This is not speculative. It follows directly from how gravity shapes time. It is a natural consequence of the structure of space-time. But travelling into the past is another matter entirely. The event horizon allows one-way travel inward. The flow of space carries you forward into the black hole's interior, but whether that interior contains paths that loop backward in time, whether it contains roads that bend so strangely they meet their own past, is a deeper question. For now, simply imagine standing at the edge of a cosmic waterfall. The current grows stronger. The air grows quiet. Your watch ticks normally in your hand. Yet far away, someone watching you sees your movements slow, stretch, and nearly freeze. Space flows. Time stretches. And at the boundary, reality becomes more subtle than we first imagined. We have reached the edge. As we linger near the edge of a black hole, there is something gently unsettling about the way time behaves. Not dramatically, not violently, but quietly, persistently different depending on where you stand. Imagine two small boats floating on a vast dark sea. One boat remains in calm water, far from any strong currents. The other drifts closer to a powerful whirlpool. The closer boat feels the water moving beneath it, circling, pulling, spiraling inward. The distant boat feels only the stillness of open water. Now imagine that both boats carry identical clocks, perfect clocks, each second measured by the steady swing of a pendulum or the regular vibration of atoms. From the perspective of the distant boat, the clock on the nearer boat appears to tick more slowly. Each second stretches slightly longer than expected. The hands seem reluctant to move. The closer the second boat drifts toward the whirlpool, the more exaggerated this effect becomes. This is not illusion. It is not malfunction. It is how gravity reshapes time. In Einstein's description of gravity, which we gently translate into words rather than equations, mass does not simply pull on objects. Instead, it curves the geometry of space and time. When mass becomes extremely concentrated, as it does in a black hole, the curvature becomes steep, and in steeply curved regions, time flows differently. The closer you move toward that steep curve, the slower your clock runs relative to a clock far away. This effect is not confined to black holes. Even on Earth, clocks at sea level tick slightly slower than clocks on mountaintops. The difference is tiny, far too small for us to notice without sensitive instruments, but it is measurable. Atomic clocks placed on airplanes, flown around the world and brought back have confirmed this effect. Satellites orbiting Earth must account for it constantly. Without those corrections, navigation systems would drift off course within days. So gravitational time dilation is not theoretical poetry. It is part of our daily technology. Near a black hole, however, the curvature becomes extreme. Let's imagine lowering a clock toward the event horizon on an impossibly strong cable. From far away, you watch its ticking through a telescope. At first, it seems normal, but as it descends, the ticking slows. Each second takes longer. The motion grows languid. The light coming from that clock also changes. Light carries energy, and when light climbs away from strong gravity, it loses some of that energy. Losing energy means its wavelength stretches. Its colour shifts toward the red end of the spectrum. It is similar to the way the sound of a siren changes pitch as it moves away from you, growing lower and softer. Except here, it is not motion through air causing the change. It is gravity stretching the very rhythm of light. As the clock approaches the event horizon, the stretching becomes extreme. The ticking seems almost to halt. The light becomes so red, so faint, that it eventually fades from view. To you, watching from a safe distance, the clock never quite crosses the boundary. It hovers, frozen at the edge, and yet, from the perspective of the clock itself, from the traveller holding it, nothing peculiar happens at that precise boundary. No wall is encountered, no dramatic flash. The crossing feels ordinary. This duality is one of the most subtle aspects of relativity. Both observers are correct within their own frames of reference. The laws of physics do not privilege one viewpoint over another. Time is not a universal river flowing at the same rate everywhere. It is more like a landscape with slopes and valleys. In deeper valleys, it flows more slowly relative to higher ground. This leads to a remarkable possibility. If you could hover near a black hole, not crossing the event horizon, but remaining close to it for some time, your clock would run slower, relative to someone far away. When you eventually returned, you would find that more time had passed for them than for you. In effect, you would have travelled into the future, not by stepping through a portal, but by dwelling in a region where time flows more gently. This is not speculative fiction. It is built into the structure of space-time as described by general relativity. Astronauts on the International Space Station age slightly differently than people on Earth's surface. The difference is tiny but real. Black holes simply amplify this effect. Now, you might wonder whether this slowing continues indefinitely. Could time actually stop at the event horizon? From the perspective of the distant observer, it appears so. But the appearance is shaped by the extreme redshift of light. Signals take longer and longer to escape. The information becomes stretched thinner and thinner, like a rubber band pulled to its limit. In practice, the infalling object continues inward, crossing the horizon in finite time according to its own clock. The apparent freezing is a feature of how information travels outward, not of what the falling traveller experiences. This distinction becomes important when we consider deeper questions about what lies inside. For now, it is enough to hold this image. Two clocks, both accurate, both honest, disagreeing gently about the flow of time because they inhabit different regions of curved space-time. The universe does not require a single master clock. It allows time to be local, and once we accept that time can stretch, slow, and diverge depending on gravity, the idea of travelling forward in time no longer seems impossible. The greater mystery lies not in moving forward, which gravity already permits, but in bending backward. To explore that, we must move beyond the event horizon and consider what rotating black holes might allow. For in those spinning depths, geometry becomes stranger still. As we stand at the edge of a black hole, at that invisible waterfall where space itself flows inward faster than light can climb out, we arrive at a question that has quietly troubled physicists for decades. If you were to fall toward the event horizon, would you feel anything unusual as you crossed it? According to Einstein's theory of general relativity, The answer is gentle and almost surprising. If the black hole is large enough, especially a supermassive one millions or billions of times heavier than our Sun, you might cross the boundary without noticing anything dramatic at that exact moment. There is no solid surface there, no physical wall. The event horizon is simply a mathematical boundary, defined by the behavior of light and gravity. From this viewpoint, crossing the event horizon is like stepping across a line painted on the ground. The line matters for geometry, but not for sensation. The true danger lies deeper inside, where gravity eventually stretches and compresses anything, falling inward. But another line of reasoning suggests something very different. To understand the tension, we need to gently introduce the black hole information paradox. In ordinary physics, information is never truly destroyed. If you burn a book, the pages turn to ash and smoke. The ink disperses, the structure is lost. But in principle, if you could track every molecule, every particle, the information about the book's arrangement is still encoded in the motion of those particles. The laws of quantum mechanics are reversible in this sense. If you could rewind every particle's motion perfectly, the ashes and smoke would reassemble into the book. It would be unimaginably difficult in practice, but not forbidden in principle. This idea, that information is preserved, is deeply woven into quantum theory. Now consider a black hole. If something falls into a black hole, a book, a star, a spacecraft, and if nothing ever emerges again, it seems as though as information about that object has been erased from the universe, swallowed permanently. But that contradicts the principles of quantum mechanics. In the 1970s, Stephen Hawking showed that black holes are not entirely black. They emit a faint glow due to quantum effects near the event horizon. This radiation is incredibly weak for large black holes, but over vast stretches of time, it causes the black hole to slowly lose mass and eventually evaporate. This glow is now known as Hawking radiation. Here is where the paradox deepens. If a black hole can eventually evaporate completely, and if the radiation it emits carries no detailed information about what fell inside, if it is simply random, then the information about the fallen object would truly disappear. Quantum mechanics insists that information cannot vanish. General relativity on its own seems to allow it. Two beautiful theories, each astonishingly successful, give conflicting answers. This conflict gave rise to an unsettling possibility known as the firewall hypothesis. Some physicists propose that perhaps the event horizon is not smooth after all. Perhaps quantum effects pile up at the boundary in such a way that an infalling observer would encounter a wall of extreme energy, a firewall. Instead of drifting gently across the horizon, you would be incinerated at the threshold. The name is dramatic, but the idea arises from serious reasoning. If information must be preserved, and if Hawking radiation carries it away over time, then perhaps the event horizon cannot remain empty and uneventful. Perhaps it becomes a place where quantum entanglement is disrupted in a violent way, breaking the smooth geometry predicted by general relativity. In softer language, imagine two maps of the same landscape. One map, drawn by general relativity, shows a smooth valley leading quietly downward. The crossing of the horizon is uneventful. The other map, drawn by certain interpretations of quantum theory, suggests a barrier at the edge, a boundary where the rules change abruptly. Both maps are drawn by careful mathematicians. Both are grounded in decades of evidence, yet they disagree about what happens at that precise boundary. No one has fallen into a black hole and returned to tell us which map is correct. So physicists continue to explore possible resolutions. Some suggest that information is encoded in subtle correlations within Hawking radiation, that over time, the radiation is not truly random, but carries faint imprints of what fell inside. Others propose that information may be stored on the surface of the event horizon itself, like patterns etched into an invisible membrane. Still others argue that the paradox signals something deeper, that neither general relativity nor quantum mechanics is complete on its own, that a more fundamental theory, often called quantum gravity, must reconcile the two. For our question about time travel, this debate matters deeply. If the event horizon is smooth, then falling inward may allow access to regions of space-time where strange geometries exist, possibly even paths that loop in time. If the horizon is instead a destructive boundary, then such journeys would be cut short before they begin. The firewall debate is not merely academic. It speaks to whether the interior of a black hole is accessible in principle or sealed off by violent quantum effects. For now, the universe remains quiet on the matter. What we know is this: general relativity describes gravity as the curvature of space-time. Quantum mechanics describes particles and information as fundamentally reversible at the smallest scales. When we combine these ideas in the extreme environment of a black hole, tension arises. That tension is not a failure. It is a sign that we're exploring the edge of our understanding. Standing here, at the threshold between smooth descent and possible fire, we feel the uncertainty not as alarm but as wonder. Two theories, each profoundly successful, whisper different stories about what lies beyond the horizon. And somewhere in that whisper, perhaps, lies the answer to whether time itself can be bent backward, or whether the universe protects its past with quiet, unbreakable laws. As we imagine drifting past the event horizon, a quiet question rises almost automatically. Would you survive the fall? The word often used in documentaries is dramatic, spaghettification. It describes the stretching of an object by extreme tidal forces. But beneath the theatrical name lies a simple idea. Gravity does not pull equally on all parts of an object when that object spans a region where gravity changes rapidly with distance. If your feet are closer to the black hole than your head, your feet feel a slightly stronger pull. The difference may be small at first, but near a compact, very dense black hole, that difference can grow immense. Imagine standing on the edge of a steep cliff. One step forward and the ground drops sharply beneath you. The change in height between where your feet stand and where your head rests is sudden and dramatic. The slope is unforgiving. Now imagine instead walking into a broad valley. The ground descends gently. You still move downward, but the change between your feet and your head is gradual. The slope is wide, not abrupt. Both landscapes may lead to the same depth, but the experience is very different. This is the key difference between small stellar black holes and enormous supermassive ones. A stellar black hole forms when a massive star collapses under its own gravity. Its mass may be several times that of our Sun, compressed into a region only a few tens of kilometers across. That means its gravity changes extremely rapidly over short distances. The slope is steep. If you were to approach the event horizon of such a compact black hole, the difference in gravitational pull between your feet and your head could become catastrophic even before you cross the boundary. The stretching would intensify quickly. The cliff is sharp, but a supermassive black hole, the kind that sits at the center of galaxies, is different. Although it contains millions or billions of times the mass of our Sun, it is spread over a far larger region. The radius of its event horizon grows in proportion to its mass, so as the black hole becomes more massive, its horizon becomes larger as well. This creates a surprising effect. At the event horizon of a supermassive black hole, the tidal forces, the difference in gravitational pull between your feet and your head, can be relatively gentle. The slope is broad. You could, in principle, cross the event horizon of a very large black hole without being torn apart immediately. It is still an irreversible journey, but the crossing itself might feel uneventful. To understand this more intuitively, imagine two mountains. One is small but extremely steep, rising sharply over a short distance. The other is vast and massive, but its sides slope gradually for many kilometers before reaching the summit. The small mountain feels more abrupt under your feet. The large one may be far taller, but the gradient is smoother. This is not because gravity is weaker in a supermassive black hole. In fact, the total gravitational influence is enormous. But what matters for tidal stretching is not only the total gravity, it is how quickly gravity changes over distance. In the language of physics, tidal forces depend on the gradient of gravity, not just its strength. But instead of focusing on derivatives and equations, we can hold on to the valley in the cliff. For a small black hole, the cliff is sharp. For a large one, the descent at the horizon is more like a wide valley. Of course, deeper inside, conditions become more extreme. Eventually, as you approach the central region, tidal forces would intensify dramatically. The stretching becomes unavoidable. But the important point for our journey is this. Not all black holes are equally hostile at the boundary. This matters because when we speak of time loops and exotic geometries inside rotating black holes, we must imagine a traveller who survives long enough to encounter those regions. In a small black hole, survival past the horizon is unlikely. In a supermassive one, at least in principle, the first steps inward might feel surprisingly calm. It is a subtle and counterintuitive result. The larger the black hole, the gentler the crossing, at least initially. Gravity stretching you like warm taffy is a vivid image, but near a vast supermassive horizon, that stretching can begin softly. The difference between your feet and your head grows slowly, not instantly. And here is another quiet detail. When we describe falling into a black hole, we often picture a non-rotating one, perfectly spherical, silent, still. But in reality, most black holes likely rotate. They inherit angular momentum from the matter that formed them. Gas spirals inward, stars orbit before collapsing, spin is almost inevitable, and rotation changes everything. A rotating black hole does not simply curve space inward symmetrically. It drags space around with it. The region just outside the event horizon becomes twisted, as though space-time itself were being stirred. Before we venture into that spinning geometry, it is important to hold on to the sense of scale we have built. Black holes are not uniform traps. Their behavior depends on mass and rotation. Their horizons are not walls but boundaries defined by the flow of space, and the experience of falling inward depends on how steeply gravity changes across your body. Standing now at the threshold of a rotating giant, imagine that the valley we spoke of does not descend straight down. Instead, it begins to curve sideways, spiraling inward. The landscape is no longer only steep, it begins to turn, and in that turning, geometry will become stranger than even the waterfall at the edge. Up until now, we've imagined black holes as still, like deep wells carved into the landscape of space-time. But in reality, stillness is rare in the universe. Stars spin, planets spin, galaxies rotate in vast, slow spirals, and when a star collapses into a black hole, it does not simply forget its motion, it keeps spinning. To understand why this matters, imagine placing a spoon into a jar of honey and turning it slowly. The honey near the spoon begins to move with it. Even the honey farther out feels the motion, though more gently. The rotation spreads outward, carried through the thick fluid. In a similar way, a rotating black hole drags the space around it. This effect is known in physics as frame dragging, but instead of focusing on the term, imagine standing near a colossal whirlpool in the ocean. The water near the centre spins rapidly. Farther out, the motion is slower but still noticeable. If you, though, try to remain perfectly still, the water resists. It pulls you into its motion. Around a rotating black hole, space itself behaves like that water. If you drift close enough, you cannot remain stationary relative to the distant stars. You're compelled to rotate along with the black hole's spin, not because of wind or force in the ordinary sense, but because the geometry of space-time itself is being twisted. There is a region outside the event horizon where this twisting becomes unavoidable. In this region, even light is forced to move in the direction of the black hole's rotation. It is as though space is being stirred so strongly that everything within it must participate in the motion. Imagine a carousel spinning so powerfully that even the air above it begins to swirl. Anyone hovering nearby would be carried along, unable to remain motionless. This region is sometimes called the ergosphere, but rather than holding on to the name, picture it as a distorted bubble around the black hole, a zone where standing still is no longer an option. Inside this bubble, something remarkable becomes possible. Because space is being dragged around, it becomes theoretically possible to extract energy from the black hole's rotation. If an object enters the swirling region in just the right way, it can leave with more energy than it arrived with, borrowing a little of the black hole's spin. The idea sounds like a trick, but it follows from the geometry of rotating space-time. The black hole loses a tiny bit of its rotational energy in the process. This tells us something important. A rotating black hole is not merely a static pit, it is dynamic. It stores angular momentum, the momentum of rotation, and that rotation influences the structure of space-time around it. Now we move one step deeper. Inside the event horizon of a rotating black hole, the structure of space-time becomes even more intricate. Unlike the simple, spherical geometry of a non-rotating black hole, a spinning one reshapes its interior differently. Earlier we spoke of falling inward like descending into a valley, but when rotation is involved, the valley curves sideways, the descent becomes spiral rather than straight. Picture a slide in a playground that not only slopes downward but twists as it descends. You're carried not only inward, but around. This twisting changes the internal geometry profoundly. In the simplest case, a non-rotating black hole, the singularity at the center is often imagined as a point, an infinitesimal region where density becomes extreme and our current equations break down. But in a rotating black hole, the singularity is described differently. Instead of a point, it takes on the shape of a ring. This detail may sound abstract, but it opens the door to deeper possibilities. Before we explore that ring, it is important to note something gentle but crucial. Everything we are describing inside the event horizon remains theoretical. We cannot observe it directly. No signal can escape from within to confirm the internal structure. The geometry is derived from mathematical solutions to Einstein's equations, relationships that describe how mass and energy curve space-time. Instead of writing those equations out, imagine them as a set of instructions for how the fabric of reality bends in the presence of mass and motion. When we include rotation in those instructions, the shape that emerges inside the black hole becomes more complex. The rotation creates not only one boundary but potentially multiple layers, like shells within shells. Between these layers, space-time behaves in unusual ways. Paths through space and time begin to curve in directions that are difficult to picture with everyday intuition. Yet we must move carefully. The presence of these strange geometrical features does not automatically mean that time travel is possible. It means that the internal map of space-time becomes richer and more intricate. Imagine opening a book and discovering that the pages are not flat but folded and curved. Looping back on themselves, the text may appear to double or overlap, but whether you can step from one line to another is another matter entirely. In the next stage of our journey, we will examine that ring at the centre, the rotating singularity, and the surprising paths that geometry allows around it. For now, simply rest with this image, a vast, spinning darkness in the centre of a galaxy. Space around it not only falling inward, but turning. A whirlpool not of water, but of space-time itself. The descent is no longer straight, it curves, and in that curvature, time may behave in ways that challenge everything we assume about past and future. As we move inward through the spinning geometry of a rotating black hole, we arrive at one of the most unusual features predicted by Einstein's equations. Earlier, we imagined the centre of a non-rotating black hole as a point, an infinitesimal region where density becomes extreme and our current understanding breaks down. But when the black hole spins, the mathematics describe something different. Instead of a point, the singularity forms a ring. Picture a loop, like a thin circular wire suspended in darkness. Around this ring, the structure of space-time is not merely curved downward, it is twisted and folded in ways that challenge everyday intuition. Now, we must proceed gently. The word singularity does not mean a solid object. It does not mean a metal ring floating in space. It represents a place where our equations predict infinite curvature, a signal that the theory, as it currently stands, is incomplete at that extreme. Still, within the mathematical description, the rotating black hole contains this ring-shaped region, and around that ring something extraordinary appears in the geometry. Certain paths through space-time, when traced carefully in the equations, curve back toward their own past. In physics, these are called closed time-like curves, but instead of holding on to that phrase, let us translate it into something softer. Imagine walking along a road that bends gradually to the left. You continue walking. The road curves more sharply. You do not notice at first how much it has turned. After a long while, you realize something impossible. You're approaching the place where you began, but from behind yourself. The road has curved so strangely that it meets its own past. In ordinary life, time feels like a straight line. Yesterday is behind us. Tomorrow lies ahead. We cannot step backward along the timeline. We cannot revisit earlier moments. But in the geometry of a rotating black hole, the mathematical map allows for paths where the direction of time tilts and bends. If you followed one of these paths precisely, the coordinate describing forward in time would gradually shift direction. It is as though time, which normally points steadily ahead, like a compass needle, begins to rotate as you move through space. This does not mean that time stops. It does not mean you can casually step into yesterday. It means that the structure of space-time, as described by the equations, permits loops. To picture this more gently, imagine drawing a straight line on a sheet of paper. That line represents your path through time. Now fold the paper carefully until two distant points on the line touch. If you could move through the fold instead of across the surface, you might travel from a later point to an earlier one without retracing the line. The rotating black hole's interior, in its mathematical description, contains folds like this. But here's the crucial distinction. A mathematical possibility is not automatically a physical reality. The equations of general relativity are incredibly successful. They describe the bending of light around stars, the expansion of the universe, and the merging of black holes detected by gravitational wave observatories. Yet they are classical equations. They do not include the quantum effects that become important at very small scales and extreme densities. When we follow the classical geometry all the way to its limit, we discover these loops. But near the singularity, quantum gravity, a theory we do not yet fully possess, must become relevant. It is possible that quantum effects would destabilize these looping paths before any traveler could use them. it is possible that the interior geometry is far more chaotic than the smooth mathematical solution suggests. There is also another subtlety. Even within the classical picture, the region where these time loops appear lies beyond layers of intense gravitational behaviour. Earlier we spoke of the twisting region outside the event horizon. Inside there may be multiple boundaries, layers where the direction of time and space exchange roles. Crossing into those deeper regions would require surviving conditions that may be violently unstable. So when we speak of time loops inside a rotating black hole, we are describing what the equations allow under idealized conditions. We are not describing a proven cosmic corridor waiting to be entered. Still, the fact that such loops appear at all is remarkable. It tells us that time is not fundamentally protected from bending in the mathematical structure of general relativity. The laws do not forbid these strange curves outright. They permit them. This is where the tension with entropy and quantum mechanics will later return. For while the geometry may allow loops, the broader laws of thermodynamics and quantum information may resist them. For now, let us linger with the image. A spinning darkness at the centre of a galaxy. Inside it, a ring where the curvature becomes extreme. Around that ring, paths that bend not only through space but through time itself. You walk forward, the landscape curves, the direction of later tilts, and somewhere in that twisted geometry, the map suggests you could arrive before you departed. Whether nature truly permits such a journey is another question entirely. But the mathematics opens the door, quietly, elegantly, to the possibility that time is not always a straight road. Sometimes, in the deepest curves of space-time, it may loop. As we reflect on the possibility of paths inside a rotating black hole that bend back toward earlier moments, it is natural to wonder whether there might be an easier route, one that does not require descending all the way into a singularity. This is where the idea of wormholes enters our story. Nearly a century ago, when Einstein's equations were still new, Einstein and Nathan Rosen discovered that the mathematics allowed something intriguing, a bridge connecting two distant regions of space-time. The solution described a kind of tunnel, a shortcut between separate points. To picture it gently, imagine holding an apple in your hand. Suppose a tiny worm wants to travel from one side of the apple to the other. It could crawl across the curved surface, taking the long route, or it could burrow straight through the apple's interior, emerging on the opposite side much more quickly. A wormhole is like that tunnel through the apple. Instead of moving across the curved surface of space-time in the ordinary way, you pass through a shortcut that connects distant points directly. Now imagine space-time not as emptiness, but as a flexible fabric or a vast landscape. Two regions that appear far apart when measured along the surface might lie close together if the fabric were folded. If you could step through the fold instead of walking across the surface, you would arrive much sooner. In the original solution proposed by Einstein and Rosen, this bridge connected two black holes. However, their version of the bridge was not traversable. It would pinch off too quickly for anything to pass through. Later, other physicists explored whether a wormhole could be held open long enough for travel. And in the mathematics, under very specific conditions, it appears possible, at least in theory. But holding such a tunnel open requires something unusual. Under normal circumstances, gravity pulls inward. It draws matter together. If you dig a tunnel in wet sand, the walls collapse because gravity presses inward from all sides. To keep a wormhole stable, the mathematics suggests you would need a form of energy that behaves differently, something that pushes outward, counteracting gravity's inward pull. This is sometimes described as negative energy. But instead of focusing on the term, imagine a strange scaffolding that exerts pressure outward rather than inward. It does not attract, it repels. In quantum physics, tiny fluctuations of this sort can appear briefly in very small regions. Experiments involving closely spaced mirrors have shown that under certain conditions the energy between them can dip slightly, below what we would normally consider empty space, but these effects are minuscule and fleeting. Scaling such phenomena to hold open a macroscopic tunnel across cosmic distances is another matter entirely. Still, the idea remains mathematically intriguing. And here is where wormholes intersect with time travel. Suppose, purely hypothetically, that you had a stable wormhole with two mouths, two openings connected by a tunnel through space-time. At first, both mouths are synchronized in time. If you step through one, you emerge at the other at the same moment. But now imagine moving one mouth of the wormhole at extremely high speed relative to the other, or placing it near a strong gravitational field for some time. From earlier sessions, we know that motion and gravity affect the flow of time. A clock travelling near the speed of light ticks more slowly than a stationary one. A clock near intense gravity ticks more slowly than one far away. If one mouth of the wormhole experiences this time dilation while the other remains stationary, the two ends will no longer agree on the passage of time. Picture two identical clocks. You take one on a long, fast journey through space, then bring it back. When reunited, that travelling clock shows less elapsed time. It has aged less. Now imagine each clock attached to a mouth of a wormhole. If one mouth undergoes this journey while remaining connected through the tunnel, then stepping through the wormhole could allow you to emerge at a time earlier than when you entered, relative to the external universe. The key idea is this: time dilation does not break the wormhole's internal connection. The tunnel links the two mouths in a way that preserves their internal synchronization, even as their external timelines drift apart. So while no one is reversing time locally, the relative shift between the mouths could create what looks like backward time travel. It sounds like science fiction. But the reasoning follows directly from two established principles: the bending of space-time and the relativity of time. Yet we must remain careful. Every step in this chain of reasoning depends on the existence of a stable, traversable wormhole, something we've never observed. No astronomical evidence confirms their presence. No laboratory experiment has produced one. Moreover, the exotic energy required to hold such a tunnel open may be fundamentally constrained by deeper laws of physics. The amounts needed might be unattainable, or quantum instabilities might cause the tunnel to collapse the moment it begins to function as a time machine. Still, the idea persists because it reveals something profound. General relativity does not forbid shortcuts through space-time outright. It permits them under certain mathematical conditions. Whether nature allows those conditions to manifest physically remains an open question. For now, hold the image gently in your mind: a folded map, a tunnel through an apple, two doorways, linked invisibly across space, and one doorway aging more slowly than the other. If such a structure could exist, stepping through might feel less like breaking time, and more like taking a shortcut through its hidden folds. The idea of a wormhole, a shortcut through space-time, has a quiet elegance to it. Fold the map, step through the crease, arrive somewhere distant, perhaps even at another moment in time. But elegant mathematics is one thing. Building a stable tunnel in the real universe is another. To understand why, we must return to a simple image. Imagine digging a tunnel through wet sand on a beach. As you hollow out the center, the sand above begins to sag. Gravity presses downward. The walls crumble inward. Unless you brace the tunnel with strong supports, it collapses almost immediately. Gravity, in our universe, almost always pulls inward. If a wormhole forms, even briefly, gravity from the surrounding space-time presses in on it from all sides. The tunnel wants to pinch shut. It wants to collapse. The mathematics of general relativity shows that to prevent this collapse, something must push outward from inside the tunnel. Not a solid beam, not a metal brace, but a form of energy that behaves in a very unusual way. Ordinary matter does not qualify. If you place normal matter inside the throat of a wormhole, it adds more gravitational pull, it increases the inward pressure, it helps close the tunnel rather than hold it open. What is required, according to the equations, is a kind of energy that exerts negative pressure, meaning it pushes outward rather than pulling inward. In very simplified language, it behaves opposite to normal matter. Instead of deepening the well, it props the tunnel open. Physicists sometimes call this exotic matter, but that phrase can sound dramatic. A softer way to think of it is as a form of energy that bends space-time in the opposite direction of what we're used to. Is there anything like this in nature? At very small scales, quantum theory does allow for subtle effects where energy briefly dips below what we consider empty space. These are not violations of conservation laws. They are tiny fluctuations permitted by the uncertainty built into quantum mechanics. One famous example involves two mirrors placed extremely close together in a vacuum. Under those conditions, the space between the mirrors contains slightly less energy than the space outside. This tiny difference can create a measurable force pushing the mirrors together, but the magnitude of that effect is extraordinarily small. It operates at microscopic distances. Scaling it up to hold open a wormhole large enough for a person, or even a particle, would require conditions far beyond anything we know how to create. Some people wonder whether dark energy could play this role. After all, dark energy is thought to drive the accelerated expansion of the universe. It behaves differently from normal matter, exerting a kind of outward influence on cosmic scales. However, dark energy appears to be spread extremely thinly throughout space. Its density is very small. It influences the universe only when averaged across vast distances between galaxies. Concentrating it in a small region to stabilize a wormhole seems incompatible with what we observe. So while dark energy gently pushes the universe apart over billions of years, it does not appear to be the kind of concentrated scaffolding required to prop open a tunnel through space-time. There's another complication. Even if some outward-acting energy could exist in sufficient quantity, wormholes are notoriously unstable. Small disturbances, a passing particle, a ripple of radiation, could trigger feedback effects that cause the tunnel to collapse. Picture two hands pushing outward against a heavy door that gravity is trying to slam shut. The hands must press continuously and precisely. If the pressure wavers even slightly, the door swings closed. In the mathematics, tiny fluctuations can amplify rapidly near a wormhole's throat. The very attempt to send matter or information through the tunnel may destabilize it. This leads to an important philosophical point. General relativity permits wormholes under certain idealized conditions. It does not forbid them outright. But the additional requirements, exotic energy, stability against quantum fluctuations, may be so restrictive that nature never realizes them. It is as if the blueprint allows a doorway, but the building materials available in our universe cannot sustain it. And here, our earlier discussion of entropy quietly returns. If time travel to the past were possible through a stable wormhole, it would introduce the possibility of paradoxes. You could, in principle, influence events that led to your own journey. You could send information backward in time. Some physicists suspect that the laws of physics may conspire to prevent such paradoxes. Stephen Hawking once proposed what he called a chronology protection conjecture, the idea that the universe prevents the formation of closed time loops at macroscopic scales, not through dramatic explosions or visible barriers, but through subtle instabilities that destroy the necessary conditions before they can mature. In this view, wormholes might form fleetingly at microscopic scales. but attempts to turn them into time machines would trigger runaway effects that collapse them instantly. The universe, in other words, may tolerate small fluctuations, but not shortcuts that rewrite history. For now, wormholes remain a theoretical possibility. They emerge from the equations like delicate arches in an architectural drawing, beautiful, symmetrical, suggestive, but without the right materials they remain drawings. Still, their existence in the mathematics tells us something profound. The geometry of space-time is flexible enough to allow tunnels. It is not rigid. It can, in principle, fold and connect distant points. Whether those folds can be stabilized is another question, one that leads us toward deeper principles governing time itself. Because even if gravity allows a shortcut, entropy and quantum information may quietly insist that the past remains fixed. The tunnel may exist in theory, but gravity keeps trying to close the door. After wandering through spinning geometries and hypothetical tunnels, it is comforting to return to something solid, something measured, tested, quietly confirmed. Time travel, in one direction at least, is not speculative. It already happens. Earlier we described how gravity can stretch time near a black hole, but that stretching is not exclusive to cosmic extremes. It happens wherever gravity exists, including here on Earth. Imagine two identical clocks, perfect clocks. One sits on the ground floor of a tall building, the other rests in the penthouse at the very top. Common sense might suggest they tick at the same rate. After all, the difference in height is small compared to the size of Earth. Yet according to general relativity, the clock closer to Earth's centre, the one on the ground floor, experiences slightly stronger gravity. And in stronger gravity, time flows a little more slowly. The clock in the penthouse, feeling slightly weaker gravity, ticks just a bit faster. The difference is unimaginably tiny, far too small for a human to notice, but atomic clocks are precise enough to detect it. Atomic clocks do not rely on swinging pendulums or mechanical gears. They measure time by observing the natural oscillations of atoms, steady, predictable rhythms embedded in the structure of matter itself. These oscillations are so consistent that even tiny shifts in gravitational strength alter their timing. Experiments have placed atomic clocks at different altitudes, on mountains, in airplanes, even separated by only a few centimeters in laboratory conditions. Every case, the clock positioned slightly higher ticks slightly faster. Gravity stretches time. Now let us widen the scale. Satellites orbiting Earth float thousands of kilometers above the surface. They experience significantly weaker gravity than we do. As a result, their clocks tick faster than clocks on the ground. But satellites are also moving very quickly, and motion itself affects time, a point we will explore more deeply soon. When engineers design the global positioning system, the network of satellites that allows your phone to determine your location, they must account for both gravitational time dilation and motion-based time dilation. If they did not correct for these effects, the system would drift off course by kilometers within days. In other words, every time your phone shows you a map and a blue dot marking where you stand, it is quietly relying on Einstein's theory of relativity. Time does not flow identically everywhere, it depends on gravity. Now imagine amplifying this effect. Earth gravity is gentle compared to that of a black hole. Near a supermassive black hole, the stretching of time becomes dramatic. A clock hovering close to the event horizon might tick far more slowly relative to one far away. If a traveller could approach such a region safely, remain there for a period, and then return to distant space, they would discover that much more time had passed for others than for them. They would have travelled into the future, not through magic, not by breaking laws, but by dwelling where time flows differently, To understand this softly, imagine time as a river flowing across a landscape. In shallow regions, the water moves quickly. In deep valleys, it flows more slowly. Two boats drifting in different parts of the river will not cover equal distances in equal moments. Gravity shapes the riverbed of time. The deeper the valley carved by mass, the slower the current. What makes this so remarkable is that it is not just theoretical. It has been tested repeatedly. Clocks flown on aircraft returned slightly out of sync with those that remained on the ground. Satellites must be adjusted. Laboratory experiments confirm that raising a clock by a small height changes its rate. Time travel to the future is woven into the fabric of physics. Of course, the amounts involved in everyday gravity are small. You would need extreme conditions to produce dramatic differences. But near neutron stars or black holes, the effect becomes profound. It is important to pause here and notice something subtle. Nothing in these observations allows travel to the past. Gravity slows time relative to distant observers. It does not reverse it. It does not create loops on its own. If you linger in stronger gravity and then return, you move forward relative to others. You never step backward, and this asymmetry hints at something deeper, something we'll soon explore when we speak of entropy. For now, rest with the reassurance that relativity is not an abstract curiosity. It is a measured feature of reality. Two clocks at different heights do not agree. Satellites above Earth tick at a different rate than clocks below. Time is local. It bends gently in the presence of gravity, and in bending it allows one-way journeys into the future. Journeys already quietly happening around us, every day without fanfare. The universe does not forbid time travel entirely. It simply seems to guide it in one direction. After travelling through spinning singularities and hypothetical tunnels through space-time, it is soothing to return to something solid, something measured, tested, and woven quietly into the technology we use every day. Time travel in one direction at least is not speculative. It is already happening. We saw earlier that near a black hole, clocks slow down relative to those far away. But the same principle applies even here on Earth, just in a much gentler form. Gravity affects time. The stronger the gravitational field you inhabit, the more slowly your clock ticks compared to someone in weaker gravity. Imagine a tall building in a city. In the basement, gravity is ever so slightly stronger than on the rooftop. The difference is tiny, almost unimaginably small, but it exists. If you placed one extremely precise clock in the basement and another identical clock in the penthouse, the clock upstairs would tick just a little faster, not by seconds you could feel, not by anything noticeable in daily life, but measurable. The reason is simple in spirit, even if complex in mathematics. Gravity is not merely a force pulling downward, it is the curvature of space-time caused by mass. And in regions of deeper curvature, time flows more slowly relative to regions where the curvature is gentler. You can picture it like this. Imagine space-time as a calm river. In shallow areas, the water flows freely. In deeper areas, the current moves differently. If you drift deeper into a gravitational well, the flow of time relative to someone outside becomes slower. The effect was predicted by Einstein's theory of general relativity over a century ago. But predictions in physics must be tested. In the 20th century, scientists began building atomic clocks, devices so precise that they measure time based on the vibration of atoms themselves. These vibrations are astonishingly regular. They allow us to detect differences in time measured in fractions of a billionth of a second. In one famous experiment, atomic clocks were flown aboard airplanes around the world and compared with clocks that remained on the ground. When the airborne clocks returned, they showed slight differences in elapsed time. differences consistent with both gravitational effects and motion. Later experiments placed atomic clocks at different altitudes and compared them directly. Even raising a clock by just a few tens of centimeters, roughly the height of a book, can produce a measurable difference in time when using today's most advanced instruments. That is how subtle and how real gravitational time dilation is. But perhaps the most practical demonstration of this effect orbits above us every day. The global positioning system relies on satellites circling Earth at high altitude. These satellites carry atomic clocks that continuously broadcast timing signals. Your phone receives signals from multiple satellites and calculates your position based on how long those signals take to arrive. Here is the quiet detail that matters. Satellites orbiting Earth experience weaker gravity than we do on the surface. Because gravity is weaker, their clocks tick slightly faster than clocks on the ground. At the same time, the satellites are moving rapidly in orbit, and motion also affects time, a topic we will explore more fully in the next session. The motion tends to slow their clocks relative to stationary observers. Both effects must be accounted for. Engineers calculate how much faster the satellite clocks run due to weaker gravity and how much slower they run due to their speed. The net effect is small, only microseconds per day, but if ignored, your GPS position would drift by kilometers over time. So relativity is not an abstract curiosity. It guides airplanes, it helps ships navigate, it tells your phone where you are. Time does not flow at the same rate everywhere. Near Earth's surface, time flows slightly more slowly than in orbit. Near a black hole, it would slow dramatically compared to distant regions. And this leads to something extraordinary. If you could live near a strong gravitational field, hovering safely close to a supermassive black hole's event horizon, and later return to a region far away, you would find that more time had passed for others than for you. You would have aged less. From their perspective, you would have travelled into their future. This is not fantasy, it follows directly from how gravity shapes space-time. The mathematics behind it is precise and elegant, relating mass, distance, and the flow of time. But instead of dwelling on symbols, we can hold on to the image of clocks at different depths in a gravitational well. The deeper clock ticks more slowly. Gravity bends space, and in doing so, it bends time. The key insight is that time is not universal. There is no single cosmic clock ticking identically everywhere. Each observer carries their own measure of time, influenced by motion and gravity. In daily life, the differences are too small to feel, but in extreme environments, the divergence becomes profound. And so, we arrive at a quiet but powerful conclusion. Travel into the future is already permitted by the laws of physics. It does not require wormholes or singularities. It requires only gravity or speed. The universe allows time to stretch. The deeper mystery is whether it allows time to fold back upon itself. Gravity is not the only thing that bends time. Motion does too. While general relativity tells us that gravity shapes the flow of time, special relativity, Einstein's earlier theory, reveals that speed alone can stretch or compress it. The core idea is surprisingly simple. The faster you move relative to someone else, the more slowly your clock ticks compared to theirs. Not because your clock is broken, not because time is being manipulated, but because time itself is woven together with space in a single fabric, and moving through space changes how you move through time. To picture this softly, imagine time as a wide river flowing forward. If you stand still on the shore, the current carries you steadily downstream. But if you begin swimming across the river at high speed, your motion changes how you move relative to the current. The details are subtle, but the result is clear. Moving rapidly alters the passage of time relative to others. Physicists express this relationship using a mathematical factor that depends on how close your speed is to the speed of light. As your speed approaches the speed of light, the ultimate speed limit of the universe, time for you slows dramatically relative to someone at rest. Rather than writing the formula, imagine this principle. At ordinary speeds, walking, driving, flying in an airplane, the difference is tiny, too small to notice without precise instruments. But as speed increases toward the speed of light, the stretching of time becomes enormous. This leads to one of the most famous thought experiments in physics. Two twins are born at the same time. One remains on Earth. The other boards a spacecraft capable of travelling at speeds very close to the speed of light. The travelling twin journeys through space for what feels like a few years on their own clock. Then they return home. When they reunite, something astonishing has happened. The twin who stayed on Earth has aged much more. The travelling twin is younger. No trickery. No paradox in the everyday sense. Simply the geometry of space-time revealing that motion alters the rate at which time passes. This is sometimes called the twin paradox, though it is not truly a paradox once the details are understood. The key is that the travelling twin changes frames of reference when turning around to return, while the earthbound twin does not. But rather than dwelling on frames and transformations, let us hold on to the image. One twin takes a journey near light speed. Their clock ticks more slowly relative to the one who stays behind. When they return, they have leapt into the future of those who remained. Again, this is not speculative fiction. Particles called muons, unstable particles produced when cosmic rays strike Earth's atmosphere, provide experimental confirmation. Muons decay quickly when at rest, but when travelling at extremely high speeds toward Earth's surface, they survive longer than expected. Their internal clocks slow down, relative to us. Without time dilation, many of these particles would decay before reaching the ground. Yet they are detected in abundance. Nature itself performs the experiment, and just as with gravitational time dilation, engineers must account for motion-based time dilation in satellite systems. The combination of gravity and speed subtly alters the ticking of clocks in orbit. All of this leads to a gentle but profound conclusion. The universe allows travel into the future. If you travel fast enough or dwell in strong gravity long enough, you can arrive in a distant future relative to those who did not share your journey. You cannot skip backward. You cannot revisit yesterday, but you can leap forward. It may require extreme technology to achieve dramatic effects, spacecraft capable of sustaining speeds near light or proximity to powerful gravitational fields, but the principle is embedded in the structure of space-time. Time is not absolute, it is local and relational. Each observer carries their own measure of time shaped by motion and gravity. You might imagine two clocks drifting on different currents of the same river. They remain connected to the same overall flow, yet they do not advance at identical rates, and there is something quietly comforting about this. Time travel to the future is not forbidden, it is simply difficult. It does not violate the laws of physics, it expresses them. The deeper mystery remains the other direction. Why does time seem to resist flowing backward? Why does it stretch, but not reverse? To understand that, we must turn away from relativity for a moment and look at something more familiar, a broken coffee mug on the floor. So far we have seen that time can stretch. Gravity slows it, speed slows it. Under the right conditions, you can step forward into someone else's future. But in all of these examples, something remains constant. Time always moves forward. You may age more slowly, you may arrive in a distant future, but you never reverse direction. To understand why, we must leave black holes and spacecraft behind for a moment and look at something far more ordinary. Imagine holding a warm coffee mug in your hands. The ceramic is smooth. The handle rests comfortably between your fingers. Steam rises gently from the surface. Now imagine the mug slips. It falls. It strikes the floor. It shatters into dozens of fragments. The sound is sharp. The pieces scatter outward. Some slide across the tiles. Some remain still. We've all seen this happen. What we've never seen is the reverse. We have never watched shards leap from the floor, glide across the room, click together perfectly and rise into our hands as a whole mug again. The laws of physics that govern the motion of atoms do not forbid such a reassembly in principle. At the microscopic level, the fundamental equations describing motion are largely symmetric in time. If you film the movement of atoms in isolation and played it backward, the motion would still obey the same basic rules. Yet in daily life, shattered mugs do not reassemble. This brings us to entropy. Entropy is a measure of how many different microscopic arrangements correspond to a given macroscopic state. But instead of holding on to that formal definition, imagine it like this. There are many more ways for a mug to exist as scattered fragments than as a single intact object. There are vastly more ways for cream to be mixed into coffee than for it to remain neatly separated after being stirred. There are countless ways for confetti to be dispersed in the air, and almost no ways for it to spontaneously gather into a tidy pile. In simple terms, disorder is statistically favoured. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase over time. Not because of a mysterious force pushing things toward chaos, but because there are overwhelmingly more configurations that correspond to what we call disorder. Imagine shuffling a deck of cards. There's only one arrangement that counts as perfectly ordered by a specific rule. Say, all hearts in sequence, followed by all spades, and so on. But there are astronomically many ways for the deck to be mixed. If you shuffle randomly, you will almost certainly end up with a mixed deck. The chance of accidentally returning to the precise original order is unimaginably small. The same statistical logic applies to broken mugs and scrambled eggs. When a mug shatters, its atoms rearrange into one of the countless possible disordered configurations. For those fragments to spontaneously reassemble would require an incredibly precise coordination of atomic motion, one arrangement out of an almost incomprehensible number of possibilities. It is not forbidden by the microscopic laws, it is simply overwhelmingly unlikely. Entropy gives time its arrow. While the equations of motion for individual particles may allow time reversal, the collective behaviour of trillions upon trillions of particles overwhelmingly favours increasing disorder. You can stir cream into coffee and watch the pale swirls dissolve into brown, but you cannot unstir it, not because a law forbids it directly, but because the number of ways for the cream and coffee to be mixed far exceeds the number of ways for them to remain separated. Time feels one-directional because entropy increases. You age, wood burns, ice melts, stars radiate energy. Each process increases entropy in the surrounding universe. If backward time travel were possible at a macroscopic scale, it would imply reversing these entropy increases. It would mean restoring shattered mugs, unburning wood, unmixing cream from coffee. It would require guiding the positions and motions of countless particles back into highly ordered configurations. And that is where the tension appears. Relativity allows time to stretch and slow. Wormhole mathematics allows hypothetical loops, but entropy seems to insist that large-scale processes move in one direction. It does not absolutely forbid microscopic reversals. At tiny scales and over short times, small fluctuations can momentarily decrease entropy locally, but across everyday scales, the statistical tide flows forward. Think again of the river. In relativity, gravity and motion change the speed of the current. In thermodynamics, entropy sets the direction. The river flows downstream. You may drift at different speeds depending on where you are, but the overall direction remains, and this simple, familiar observation, a broken mug that does not repair itself, may be more powerful than any exotic geometry inside a black hole. The arrow of time is written not only in equations, but in spilled coffee, scattered confetti, and the quiet aging of every living thing. The deeper question now becomes this: why did the river begin flowing in that direction at all? If entropy gives time its arrow, then another question quietly follows. Why was entropy ever low to begin with? Because the second law of thermodynamics does not say that entropy must always increase without limit from randomness. It says that entropy tends to increase from whatever state the system starts in. If the universe had begun in complete disorder, there would be no direction for entropy to grow. Yet everything we observe suggests that the early universe was extraordinarily ordered. When we look far into space, we're also looking back in time. The light from distant galaxies has travelled for billions of years to reach us, and when we observe the faint glow of the cosmic microwave background, the lingering radiation from the early universe, we see something remarkable. The early universe was astonishingly smooth. Temperature variations were tiny. Matter was distributed almost uniformly. On large scales, it resembled a calm, nearly featureless sea. At first glance, that might sound like disorder, but in gravitational systems, smoothness corresponds to low entropy. Here is why. Gravity causes matter to clump together. It pulls gas into stars. It draws stars into galaxies. It gathers galaxies into clusters. A smooth universe, evenly spread out, has enormous potential for structure. There are many ways for matter to clump, collapse, and form complexity. As gravity works over billions of years, entropy increases. Stars ignite. They fuse lighter elements into heavier ones. They radiate energy outward into the cold of space. Eventually they burn out, leaving behind remnants: white dwarfs, neutron stars, black holes. Each of these processes increases entropy. You can picture it like a tightly wound spring at the beginning of time. The early universe held enormous gravitational potential, like a spring coiled and ready to release. Over cosmic history, that spring has been slowly relaxing. Galaxies form, stars shine, black holes grow, energy spreads outward, the universe exhales, entropy increases. But why was the spring wound so tightly in the first place? This is one of the deepest open questions in physics. The Big Bang was not merely hot and dense. It was highly ordered in terms of gravitational configuration. If the matter in the early universe had been arranged in a more typical high-entropy configuration for gravity, heavily clumped, already collapsed into black holes, then there would have been little room for entropy to grow. Instead, it began smooth. From that smoothness, structure emerged, and from that structure, the arrow of time became meaningful. Imagine a blank sheet of paper. At first, it is smooth and flat. As you crumple it, wrinkles form. The number of possible wrinkled configurations vastly exceeds the single flat configuration. The early universe was like the flat sheet. Over time, gravity crumpled it into stars and galaxies. Each crumple added to entropy. Each collapse, each burst of radiation, each spreading of heat into colder regions moved the universe toward greater disorder. The arrow of time does not arise because microscopic laws forbid reversal. It arises because the universe began in a special state, one with remarkably low entropy relative to what was possible. From that beginning, the statistical direction was set. Disorder would grow, stars would age, mugs would shatter, cream would mix into coffee, and life itself would emerge as local pockets of order, fueled by energy flowing from hot to cold, from stars into space. And there is something quietly profound about this. The fact that you can remember yesterday but not tomorrow is connected to the early universe's smoothness. Memory itself requires entropy to increase. Recording information involves physical processes, electrical signals in neurons, chemical changes in synapses, all embedded in thermodynamic flow. The arrow of time is not just a property of distant galaxies, it is woven into every thought you have. If the universe had begun in high entropy, there would be no gradient, no flow, no direction in which change unfolds. So when we ask whether backward time travel is possible, we're not merely asking about geometry or exotic matter. We're asking whether the fundamental thermodynamic gradient that began at the Big Bang can be reversed. Can the tightly wound spring rewind itself? Can the smooth sheet become unwrinkled without careful external intervention? So far, everything we observe suggests that the large-scale behavior of the universe respects this arrow. The spring unwinds, it does not spontaneously wind tighter, and yet, at the smallest scales, the microscopic laws remain almost indifferent to direction, which brings us to a quiet tension. The geometry of space-time may allow loops. Quantum laws may not strongly prefer one direction, but entropy, born from a low entropy beginning, seems to guide the macroscopic world firmly forward. The universe began smooth. From that smoothness came stars. From stars came elements. From elements came life, and from life came the question of whether time can turn back. We have seen that the universe began in a remarkably ordered state, like a tightly wound spring. Since then, entropy has been increasing, slowly, steadily, everywhere. Stars burn their fuel. Heat spreads outward. Structures form and eventually decay. Time seems to flow in one direction. So now the question deepens. If the geometry of space-time, in black holes or wormholes, allows paths that loop backward, could entropy forbid us from ever using them? Imagine once more a cup of coffee. You pour cream into it. At first, the white ribbon curls through the dark liquid in beautiful swirling patterns. Within seconds, the mixture becomes uniform. To reverse this process would require each molecule of cream and coffee to retrace its exact path, moving with perfect coordination back to its original positions. The microscopic laws governing those molecules do not forbid such motion in principle. If you could reverse every velocity and interaction precisely, the mixture would separate again. But in practice, that precision is unattainable. There are simply too many particles involved. The number of possible microscopic arrangements that correspond to the mixed state vastly exceeds the number that correspond to the separated state. Entropy reflects this imbalance. So let us imagine that a wormhole exists. Suppose you step through and emerge at an earlier moment in time. You would carry with you a body, a brain, and memories, all of which represent highly ordered structures that form through entropy-increasing processes. Your presence in the past would introduce information that did not previously exist in that configuration. For the past to remain consistent, the entire surrounding universe would need to accommodate this intrusion without violating thermodynamic consistency. In other words, backward time travel would require not just bending space-time, but managing entropy at cosmic scales. Picture walking upstream in a widening river. Relativity allows you to move at different speeds along the current, but entropy sets the direction of flow. To walk upstream against the full widening force of the river would require immense coordination, not just for you, but for the water itself. Some physicists argue that entropy may serve as a kind of safeguard, not a conscious barrier, not a force field, but a statistical impossibility so overwhelming that macroscopic backward time travel becomes effectively forbidden. Even if a geometric loop exists, the probability of maintaining a consistent entropy decrease across a large region may be vanishingly small. There is also the issue of paradox. If you travelled back and altered events, you might create inconsistencies, effects without causes, or causes that eliminate themselves. While relativity alone does not resolve these paradoxes, entropy complicates them further. Every action you take affects countless particles. Reversing a macroscopic chain of events would require restoring all those particles to precise prior configurations. It is not just about preventing a grandfather paradox. It is about restoring shattered mugs, unburning paper, unaging stars. The arrow of time is woven into physical processes at every scale, and yet we must be careful not to overstate the case. Entropy does not forbid small local decreases. Life itself is an example. Organisms maintain order by exporting entropy into their surroundings. They build complex structures, cells, tissues, thoughts, while increasing disorder elsewhere. So the second law of thermodynamics does not say that order cannot arise. It says that total entropy in an isolated system tends to increase. If backward time travel required a local decrease in entropy, could it be balanced by a greater increase elsewhere? In principle, perhaps. But the scale involved in reversing an entire macroscopic timeline is staggering. The deeper difficulty lies in boundary conditions. The arrow of time appears tied to the low entropy beginning of the universe. That beginning sets the global direction. Reversing a large segment of time would mean re-establishing conditions that align with that original low entropy state. It would be like attempting to rewind the tightly wound spring without access to the initial mechanism that wound it. This does not prove backward time travel impossible, but it suggests that even if geometry permits it, thermodynamics may strongly resist it. Time may bend, it may stretch, it may flow at different rates. But its direction, set by entropy, seems deeply embedded in the history of the universe. Still, at the smaller scales, something curious happens. When we examine the laws governing individual particles, we find that many of them do not strongly prefer a direction at all. And there, in the subtle domain of quantum physics, the story becomes more delicate. We have seen that entropy gives time its arrow at large scales. Mugs shatter, cream mixes, stars burn their fuel, the river flows forward. And yet, when physicists examine the fundamental equations governing individual particles, they find something surprising. Many of those equations do not strongly distinguish between past and future. If you take the mathematical description of certain quantum systems and reverse the direction of time in the equations, replacing forward evolution with backward evolution, the laws still make sense. The basic structure remains consistent. To picture this gently, imagine filming a single billiard ball sliding across a frictionless surface. If you play the film backward, the motion still obeys the same basic physical rules. The ball glides smoothly. Nothing obviously impossible occurs. At the microscopic level, many interactions are like that. The asymmetry we observe in daily life, the broken mug that does not repair itself, emerges not from the fundamental laws alone, but from the enormous number of particles and the statistical nature of entropy. In 2019, a group of researchers performed an experiment that illustrates this idea in a striking way. They used a small quantum system, essentially a controlled arrangement of quantum bits, sometimes called qubits, to simulate the backward evolution of a simple state. Without writing down the governing equation, we can say this: quantum systems evolve according to a precise rule that tells how their state changes over time. If you carefully manipulate that system with external controls, you can reverse the sign of the time parameter in that rule. In effect, you can guide the system to retrace its steps. The researchers prepared a simple quantum configuration, allowed it to evolve forward for a short time, and then applied a carefully designed sequence of operations that effectively reversed its evolution. The system returned close to its original state. It was not a literal reversal of time for the entire universe. It was a controlled manipulation of a very small system in a laboratory. But it demonstrated that at the quantum level, under precise conditions, evolution can be reversed. Imagine dropping a pebble into a perfectly still pond and watching ripples spread outward. Now imagine possessing a delicate device that could adjust the motion of every water molecule involved in those ripples, nudging them just so until the waves converge back toward the center and the surface becomes calm again. At the scale of a pond, this would be impossible. There are too many molecules, too many degrees of freedom. But at the scale of a tiny, isolated quantum system, something similar can be achieved. The key word here is isolated. Entropy increases when systems interact with large environments, when energy and information spread outward in countless microscopic directions. But in a carefully controlled quantum experiment, the environment can be minimized, interactions can be limited. Within that tiny arena, time can appear to forget its direction. This does not mean that macroscopic backward time travel is easy or allowed. It means that the fundamental building blocks of reality are not rigidly stamped with an arrow. The arrow emerges statistically, and this opens a delicate possibility. If quantum laws are largely symmetric in time, could quantum effects provide loopholes in the macroscopic arrow of time? Some proposals explore whether information might be transmitted backward under certain interpretations of quantum mechanics. Others investigate whether entangled systems, pairs of particles whose states are deeply linked, might exhibit correlations that blur simple notions of cause and effect. But here we must tread gently. Quantum mechanics is subtle, its interpretations vary. Experiments confirm its predictions with astonishing precision, yet the deeper meaning of those predictions remains debated. What we can say with confidence is this: at the smaller scales, the fundamental rules do not strongly prefer forward over backward. If you isolate a tiny system, control it precisely, and shield it from environmental noise, you can make it retrace its evolution, at least approximately. But scaling that behavior up to mugs, people, or galaxies encounters the overwhelming weight of entropy. It is one thing to reverse a few qubits. It is another to reverse a universe. Still, the fact that microscopic laws are largely time-symmetric suggests that the arrow of time is not etched into the core of physics at its most fundamental level. It arises from boundary conditions, from initial low entropy, from statistical tendencies. Time may flow forward because the universe began in a special state, not because the deepest equations demand a direction. And that leaves room for curiosity. If the microscopic world can briefly forget which way time points, perhaps the story is not entirely closed. If microscopic laws are largely indifferent to direction, and if small quantum systems can briefly retrace their steps, another question emerges naturally. Could information itself travel backward? At first, this sounds dramatic, but let us approach it slowly. Imagine a book resting on a wooden table. Its pages contain words, sentences, stories. Now imagine the book is burned. The paper blackens, curls, and turns to ash. Smoke rises. Heat spreads into the air. At first glance, it appears that the information contained in the book has been destroyed, but physics tells us something more subtle. The atoms that once formed the ink and paper do not vanish. They rearrange. The pattern becomes wildly complex, scattered across ashes, air molecules, and thermal radiation. The information is not erased in a fundamental sense. It becomes dispersed and extraordinarily difficult to reconstruct. In quantum theory, this principle is expressed by the idea that the evolution of isolated systems preserves information. The underlying rules ensure that the full state of the system evolves in a way that can, in principle, be reversed. In practice, however, once information spreads into the environment, once entropy increases, Recovering it becomes effectively impossible. This brings us to a delicate frontier. Some theoretical proposals suggest that under certain quantum conditions, correlations can appear that challenge our intuitive notion of cause and effect. Entangled particles, for example, share a connection that persists regardless of distance. Measuring one influences the state description of the other, yet entanglement does not allow usable information to be sent backward in time. It does not permit signaling faster than light. The correlations respect deeper consistency rules embedded in the theory. Still, the conceptual tension remains. If quantum evolution preserves information, and if microscopic processes can be reversed, perhaps the apparent irreversibility of the macroscopic world is not fundamental. One interpretation of quantum mechanics, often called the many worlds interpretation, offers a different perspective on time and causality. Rather than imagining a single timeline that can be rewritten, many worlds suggest that the universe continually branches into multiple histories. Picture walking through a forest where the path divides repeatedly. Each choice leads down a different branch. You do not erase the path you did not take, it simply continues as a separate branch. In this view, if something like backward time travel were to occur, it might not rewrite your original past. Instead, it could create a new branch, a new timeline diverging from the moment of arrival. The paradox dissolves, not because contradictions are resolved, but because histories multiply rather than overwrite. To visualize this gently, imagine a tree growing. At first it has a single trunk. As it rises, it splits into branches. Each branch grows independently. If you step from one branch to another at a higher point, you're not altering the trunk below. You're simply occupying a different extension of growth. Many worlds does not prove that backward time travel is possible. It offers a conceptual framework in which paradoxes might be avoided. Instead of asking, "Can I change my past?" the question becomes, would my action create a different branch of reality? But even here, caution is essential. The many worlds interpretation remains one way of understanding quantum mathematics. It does not provide experimental confirmation of actual branching universes we can traverse at will. It is a lens through which the equations can be viewed. And crucially, none of these interpretations have demonstrated a method for sending usable, controllable information backward in time. The fundamental rules of quantum theory preserve consistency. They prevent signals that would violate causality in a way detectable by observers. In other words, while quantum mechanics allows strange correlations and microscopic reversibility, it guards the macroscopic order of cause and effect. The ashes of the book still contain the story in a dispersed form, but reconstructing it would require perfect knowledge of every particle involved. The branches of the tree may extend into countless directions, but stepping between them remains speculative. So where does this leave us? Quantum physics loosens the strictness of time's arrow at tiny scales. It suggests that the underlying laws are not inherently one-directional. But when scaled to human experience, entropy and statistical reality reassert themselves. Time may not be fundamentally one way at its core, yet for beings embedded in thermodynamic flow, it feels profoundly so. Still, the map is incomplete. General relativity describes gravity beautifully. Quantum mechanics describes the microscopic world with astonishing accuracy. But the two maps are drawn in different inks, and where they overlap, inside black holes near singularities at the beginning of the universe, the lines do not yet align.